So class, we want to continue, please. We are on determining the heat of vaporization of dichloromethane given the vapor pressure versus temperature. So please check Excel on how to plot this graph. So the video before this is how to plot the graph. So we plotted the graph of temperature versus pressure, and we noticed that what we had was a curve, exponential graph, which we knew we could not get the heat of vaporization from that. So we use the linear form of the equation, which is 1 over T versus ln P, and we got the straight line graph, and we got the equation of the graph. So this is just a replay of the graph we obtained. Please check the video on how to plot the graph. So we got this graph, a linear graph, and this was our equation of the line. Sorry, this is the equation of the line, this one. Arrow square is just to tell us how the points fit well to give us a straight line graph. The closer arrow square is to 1, the better. That's a better straight line graph. So now we want to calculate the heat of vaporization. So from our calculation, this is the slope. You can put it to 2 significant figures, but I normally prefer 3. If it's 3 significant figures, you round up. So this is the slope. We are going to use the slope to calculate the heat of vaporization. So from the slope, you see, slope is delta H bar over arrow, and this is the slope. Then this is the arrow. When we do the multiplication, we notice that our answer is 31.6 kilojoules per mole to 3 significant figures. So that is how we use a graph to find the heat of vaporization. Now let's look at our classic Clapeyron equation in a case where we have just 2 points. So classic Clapeyron equation 2.4. The equation below can be used with just 2 measurements of vapor pressure and temperature to find the heat of vaporization. So this is the equation below. So you see P2, 1 over T2. P1, 1 over T1. So let's take an example. Calculate the heat of vaporization of methanol at 12 degrees Celsius. So they gave us only the 12 degrees Celsius. What is our T1? What is our T2? Normally, if I have to give you the question, I'll give you T1 and T2. But in this case, because it's like a homework, our T1 will be the normal boiling point, and our P1 will be the atmospheric pressure. Remember we said normal boiling point is the point in which the vapor pressure matches the atmospheric, 1 atmospheric pressure. So that's what we are going to do. So our T1 is 64.4 degrees Celsius. Our P1 is 760 millimeters mercury tall. Heat of vaporization is 35.2 kilojoules per mole. And T2 is 12 degrees Celsius. Please convert these temperatures to Kelvin. Convert them to Kelvin. So that's what we are going to do. We're going to convert the temperatures to Kelvin, and this is your equation to convert degrees Celsius to Kelvin. Don't forget. So that's our equation we are using. So we are converting our temperatures to Kelvin. So this is our T1 in Kelvin, and this is our T2 in Kelvin. Now we want to substitute and do our calculations. So I want to substitute now to our equation. That's our equation. So we are going to substitute. Please, we are converting our unit to, this is plus, joules, because our R is in joules. So 35.2 kilojoules, please convert it to joules. So it's 35.2 times 10 to the positive 3, not negative 3. And this is our T2 and this is our T1. When we do all this calculation here, we are going to have it as ln P2 over P1 equals to minus 2.31. Please, I want you to take note of something. E. So E ln equals to 1. So this E ln here will be equals to 1. So we are going to be left with P2 over P1 equals to E minus 2.31. So our P2 will be equals to P1 E minus 2.31. And we know our P1, so P2 will be equals to 760 tau times, let's search for, so we have circumference E minus 2.31. So we'll have times 0.09926. So our P2 will be equals to 75.4. So that is what we are going to have as our P2. So that's what we are going to have as our P2. So let's continue. So that is it. So that's our P2. So the units are correct. The size makes sense since the vapor pressure is lower at lower temperature. So please, we have another example, but I would like you to do this for extra credit. Determine the vapor pressure of water at 25 degrees Celsius, BP 100 degrees Celsius, and vapor pressure, heat of vaporization is 40.7 kilojoules. So say determine the vapor pressure. In this case, you are asked to determine the vapor pressure of water. Please, I would like you to do this as extra credit. Use your equation. Ln P2 over P1 equals to minus delta H over R times 1 over T2 minus 1 over T1. Convert all your temperatures into Kelvin. The equation is Kelvin equals to degrees Celsius plus 273 plus 15. So please use this equation to solve for, to determine the vapor pressure of water at 25 degrees Celsius. So we want to look at other phase changes. Sublimation and deposition. Sublimation, solid changes to the gases bypassing the liquid phase. Deposition, the gas changes to the liquid bypassing the liquid state. The gas changes to the solid bypassing the liquid state. So the solid and vapor phase exist in dynamic equilibrium in a closed container. Then we have melting and fusion. Melting, liquid, solid changes to liquid. So we can call it fusion. Then what is freezing? Of course, in freezing, liquid goes to the solid. So let's continue with our heating curve for these other phases. So the heating curve of a solid. As you heat a solid, its temperature increases linearly until it reaches the melting point. To calculate the energy, because the temperature change is Q equals to mass times specific capacity times change in temperature. Once the temperature reaches the melting point, all the added heat goes into melting the solid and the temperature stays constant. So this is melting. Once all the solid has been turned into liquid, the temperature can again start to rise. For example, ice to water will always have a temperature of 0 degrees Celsius at 1 atmosphere. So we are going to still do this. Q1 equals to MC delta T. Then this is Q2 equals to delta H fusion times N. Then this is Q3 MC delta T. So energetic of melting. When high energy molecules are lost from the solid, it lowers the average kinetic energy. If the energy is not drawn back into the solid, its temperature will decrease. Therefore, melting is an endothermic process. Meanwhile, freezing is an exothermic process. Melting requires input of energy to overcome attraction between the molecules. So, the amount of heat energy required to melt 1 mole of a liquid is called heat of fusion or enthalpy of fusion. Always endothermic, therefore delta H fusion is positive. Generally much less than heat of vaporization. So we can see the heat of fusions. Take note, we can use it also as conversion factor. After we have talked about heat of vaporization and heat of fusion, let's look at phase changes. A phase diagram. A phase diagram describes the different states and state changes that occur at various temperatures and pressure conditions. Regions represent states, lines represent state changes, and triple point is the temperature/pressure condition where all 3 states exist simultaneously. So let's examine the phase diagram of water. So you see these different blue shades, these are regions. So you see this is the region where you have the solids. This is the region where you have the liquids. This is the region where you have the gases. This line here, we separate the solid and the liquid, is phase change. So we call it the fusion curve. This line here, we separate the solid and the gas is sublimation. So we want to do an example now. So at 20 degrees Celsius and 72.9 atmosphere, okay, this is 72.9 atmosphere. So this is 20 degrees Celsius. You go up here. You see what we have here is a liquid. So at 56.7 degrees Celsius and 5.1 atmosphere, that's 5.1 atmosphere, and this is 56, you see we have the triple point. And the triple point, we have the solid, liquid, and gas phase. Make sure you mention it. Then 10 degrees Celsius and 1 atmosphere. This is 1 atmosphere. And where is 10 degrees Celsius? Let's assume that 10 degrees Celsius should be around here. You see, we have the gas. Then 78.5 and 1 atmosphere. 78.5 and 1 atmosphere is somewhere here. So what do we have? You see, it's phase change and it's solid and gas. So we have the solid and the gas phase. Then 50 degrees Celsius and 80.1 atmosphere. So 50 degrees Celsius. 50 somewhere here. One, is it 80 atmosphere? 80 is above here. So we can say we have the supercritical fluid. On that note, I want to thank you because we have come to the end of chapter 11, intermolecular forces of attraction. So please don't forget to answer your questions. Odd number study problems are found at the back of your textbook and the answers are there. Thank you so much.